Hello everyone, and welcome to the show. I'm Max, and this is episode 2 of PQ adic analysis in the Collatz Conjecture, a video series I am making to accompany my 2022 PhD dissertation of the same name. In episode 1, I showed you a seemingly harmless-looking formula that nevertheless produced a totally unprecedented form of convergence, one where the topology of convergence varied from point to point. By any standard, this is an incredibly bizarre finding. But these findings of mine did not come out of nowhere. Rather, they're the result of a lengthy investigation into the Collatz map and its brethren, and one that I hope I will be able to share with you in the course of this series. So in episode 2, What I Have Been Smoking Lately, I'm going to give you the rundown of not just this video series, but what my research is all about. It's going to be a bit of a broad topic, and I'm going to outline what we're going to be doing in this series and the various major results that I've achieved. I won't be stating everything fully, nor will I be providing proofs at all, but rather this is just to survey the landscape and to illustrate just how much there is waiting to be done here. It really is. There's so much. So where do we begin? Well, we begin with a troublemaker that hopefully you're all familiar with. The Collatz map C from Z to Z is the function which C of n which sends n to n over 2 if n is even, and n to 3n plus 1 if n is odd. As you all know, the infamous Collatz conjecture is the assertion that for every integer n, there exists an integer k greater than or equal to 0, such that the kth iterate of n under C is equal to 1. That little circle over there means compose, and k is the exponent for the number of times. So, rather than working with C directly, we're instead going to consider a well-known acceleration of the Collatz map, the shortened Collatz map, generally denoted in the literature by T3, which is the map that sends even n to n over 2 and odd n to 3n plus 1 over 2. This is shortened in the sense that it takes care of the fact that whenever we feed an odd number to the Collatz map, we get an even number, which we're always going to divide by 2. With this, the Collatz conjecture is the assertion that for every integer n greater than or equal to 1, there is a k greater than or equal to 0, such that applying T3 to n k times gives us 1. Note that when k is 0, this notation would turn this or any map into the identity map. So a moment's thought shows that this conjecture actually comes in two pieces. The first of these is the so-called weak Collatz conjecture, which is the assertion that the only periodic points of T3 in the positive integers are 1 and 2. A periodic point, recall, is a number which, when you apply your map a sufficiently many number of times to it, you'll get sent back to itself. So every fixed point is a periodic point, but of period 1. And also note, actually, no, never mind. So the other part is the no divergence point conjecture. A divergent point, but as the name suggests, is an input which our map will iterate to either positive or negative infinity, and the no divergence point conjecture is the assertion that no positive integer is a divergent point of T3. So, just a little bit of a background here, more about the subject than the problem itself. From a dry taxonomic perspective, these conjectures belong to the subject of arithmetic dynamics. This subject was really first established by Joe Silverman's classic text, The Arithmetic of Dynamical Systems. And in that subject, what you do is you take algebraic geometry and you apply to it the ideas of the study of dynamical systems. So recall that an algebraic variety is, generally speaking, it's the set of zeros of one or more polynomials. Many algebraic varieties also have a group structure, which makes them into an algebraic group. Probably the best example of this is an elliptic curve. In an algebraic group, there are rational functions which, when you plug in points that are on your variety, the result will be another point on the variety, and these rational maps therefore form dynamical systems that we can consider as them acting on the variety. In this approach, what you do is that there is a wonderful dictionary between the language of dynamical systems and the language of algebraic number theory and arithmetic geometry. So, for example, there's connections between periodic points and pre-periodic points, and the measurements of numerical complexity called heights, and it's a very fruitful approach that lets you do a lot of things. Unfortunately, classical arithmetic dynamics of this sort has very little to say about the Collatz conjecture. T3 is simply too far removed from the foundational algebraic structures that one uses in arithmetic geometry, like algebraic varieties, algebraic groups, and abelian varieties. And as a result, we can't apply the arithmetic of dynamical systems as Silverman would consider it. So as a result, the Collatz conjecture is not just a challenge to mathematics, but to metamathematics, that is, the practice of how we do mathematics. Mathematics is filled with difficult problems, many, if not most of which, are also important. Like in real life, one of the easiest ways for a problem to be important is for it to have multifarious connections to other subjects. This is a distinguishing feature of many of the most difficult problems in number theory, such as Fermat's last theorem, the Riemann hypothesis, and the Birch and Swinnerton-Dyer conjecture. Each of these problems enjoys context with a wide range of other questions, and their resolutions would, or in the case of Fermat's last theorem, have had major implications for other mathematical investigations. Because of these rich connections, even if we can't solve the main problems themselves, there's still going to be something useful to be gained by studying something related to them, or something maybe 1 or 2 degrees removed from the original thing. The big trouble with the Collatz conjecture is that unlike Fermat's last theorem, the Riemann hypothesis, or the Birch and Swinnerton-Dyer conjecture, there doesn't seem to be any major connections between Collatz and other areas of mathematics. Algebraic geometry is often such a site for such fruitful investigations because it combines number theory when you're investigating solutions of polynomials and Diophantine equations, but it also involves algebra because we're considering the ideals generated by polynomials. And so the more subjects that can have a say in a problem, the more approachable it is. Unfortunately, with Collatz, there is really only one subject where the conjecture possesses a clear, uncontestable connection, and that's transcendental number theory. Transcendental number theory is the study of transcendental numbers, as the name suggests. It has a variety. In the simplest case, it's just proving that numbers are transcendental, which itself is very difficult. The problem of showing that pi is a transcendental number, it was first done, I believe, in 1883 by Lindemann. It resolved the 6,000-year-old problem, or 4,000-year-old problem of squaring the circle, which is given a circle of a known area, can you, using just a straight edge and a compass, construct a square of the same area as that circle? And the answer is no. Transcendental number theory, another thing that's very big in it, is the so-called linear forms of logarithms. This is studying the absolute value of an expression like a times ln of 2 plus b times ln of 3. We want to try and figure out, as a and b vary, how small can we make the absolute value of that linear combination? And a watershed result in this subject is Baker's theorem, due to the late Alan Baker, which gives explicit lower bounds for the absolute values of such linear forms and logarithms, and Baker won the Fields Medal for using those to study the solutions of Diophantine equations. Specifically, it is known that if we can resolve the weak Collatz conjecture, this would yield a major improvement in lower bounds for the absolute value of 3 to the m minus 2 to the n, where m and n are positive integers. These bounds would be a significant improvement over the lower bounds that Baker's method yields. Unfortunately, though, this connection to transcendental number theory isn't really helpful because transcendental number theory is extraordinarily difficult as a subject in its own right, because unlike arithmetic geometry and everything that involving polynomials, where we can use the techniques of algebra, because we are in transcendental number theory, we're studying transcendental functions, exponentiation, logarithms. We can't use the machinery of commutative algebra to approach things, and so it often will involve extremely intricate analytical arguments like the ones that Baker did, which involved constructing an auxiliary function that had a very specific location and intensity of zeros that you can then examine and use complex analysis to show that you get a contradiction. So the result of all of this is that Collatz stands alone, inscrutable and unapproachable. It lacks a broader context in which it might be better and more naturally understood. The fact that Collatz suffers this problem, really, it's absolutely critical if we want to understand how the problem relates to the mathematical community as a whole. Collatz is absolutely, infamously difficult. But what makes it so difficult isn't just that it seems to be hard to do, but rather there's no meaningful way to approach it. It seems like if for some reason we could get a proof of it, it would be some extremely arcane, technical bit of brinksmanship that involves some crazy properties of the powers of 2 and 3 that don't really shine a light on what's going on in the way that, say, Galois theory shines a light on the solvability of polynomials by radicals. So one of the goals of this series of videos and my research in general is to show that Collatz is not quite as unapproachable as we've previously believed. It's still difficult, still extremely difficult, make no mistake about it. However, contrary to popular belief, I maintain that it is actually very worthwhile to study this problem just because there's so much around it waiting to be explored. As if the methods of this series end up playing a role in solving the Collatz conjecture, it will only be because of significant advances which have occurred in the interim. And well, again, one of the reasons why I'm making this video is because I want to show everyone there's a lot of stuff to be found here, and it would be wonderful to get some help delving into that. So, as in my dissertation, we're going to be basically doing a tripartite program here. I have 3 main innovations to present to you. The first of these is a novel, unifying analytic formalism for studying Collatz-type maps. This is a function which I call the Newman, which we associate to a given Collatz-type map. The function chi-q that we saw in episode 1, specifically chi3, which you get from setting q equals 3, that function is the Newman of the shortened Collatz map. So with my formalism, the questions, is X a periodic point of our Collatz-type map, and is X a divergent point of our Collatz-type map, can be restated in terms of the value distribution of this Newman function. We find that these questions are equivalent to asking, is X a value attained by the Newman? Newman comes from the Latin meaning the spirit or power abiding in a thing or place. Originally, I used the name the characteristic function, hence my use of the symbol chi, but as we'll see later, this ends up being a particularly bad choice of terminology because it conflicts with the notion of a characteristic function from probability theory, which is the Fourier transform of the probability density function of whatever random variable we're studying. And it turns out, yes, we can do that here, and there's wonderfully rich connections to probability theory, even though they might not be initially apparent what I'm doing. So that's the first thing, the Newman. Oh, I should say that the result which makes this reformulation valid is called I call it the Correspondence Principle, and it tells us that we can replace the question of studying the dynamics of our Collatz-type maps by studying the value distribution of our Newmans. The second innovation of my work is that there is my discovery of an unexpected level of depth and subtlety in an almost totally neglected area of non-Archimedean analysis. This is PQ-adic analysis, the study of functions from the P-adics to the Q-adics, where P and Q are distinct primes. The things we saw in episode 1 are an example of this unexpected level of depth and subtlety, where we have functions that are not continuous but nonetheless integrable. Functions, since they're not continuous, it means in the non-Archimedean context that they should be non-integrable as well. But it turns out, no, there's a way to integrate them, and doing so requires us to work with infinite series that converge pointwise, but whose topology of convergence varies from point to point. So all of this analytical stuff waiting to be explored, and it's amazingly, it's like by magic, this PQ-adic analysis seems to be almost tailor-made for studying Collatz-type problems. So there's a synergy here. The Collatz-type problems give us some really good guiding questions and principles to explore, and they provide us with an opportunity to test out and develop these new techniques in this area of analysis. So you can quite easily make a career out of studying the analytical phenomena independent of their relationship to the Collatz conjecture. There's a lot to be done, and again, I would very much like some help doing so. What's really cool is that PQ-adic analysis doesn't just apply to functions from the P-adics to the Q-adics. It can also apply to functions from the P-adics to some metrically complete non-Archimedean field, F, whose residue field has characteristic Q not equal to P. And so we saw by opening ourselves up to frames, we can significantly expand what's done in this subject. I can actually probably go further and say that at the end of the road, we'd probably end up with a theory of functions from an Adel valued variable to an Adel valued variable, where by Adels I mean the Adel ring of a number field, or in this, if it's an analog over a function field. If you read my frames paper, which I had linked at the bottom of episode 1, I talk about how you can potentially reframe frames in terms of Adel-valued functions, which may be a potentially fruitful approach. So 1 and 2 are that, but what's 3? So 3 is the fact that in 2, we can do Fourier analysis. And in particular, this allows us to take 1 and reformulate Collatz-type problems in terms of non-Archimedean spectral theory, which is a very impressive sounding term whose meaning I'm going to explain at the moment. So, but first, before I continue, there is a caveat asterisk that I need to mention. So when I say that we're going to be reformulating the problem of studying the Collatz-type maps dynamics, there's a subtlety here, is that, as we saw, this comes in 2 parts: the weak Collatz conjecture and the no divergent points conjecture. At the moment, the weak Collatz conjecture has been fully reformulated. More generally, for any type of Collatz-type map for which my method applies, we can completely replace the study of its periodic points with the study of values attained by the map's Newman. With divergent points, however, it's only halfway done. I've shown that, here's an example, with chi3, the Newman of T3, I've shown that chi3 produces a sufficient condition for an integer to be a divergent point. However, I have not yet been able to prove the converse, that this sufficient condition is also necessary, and that every divergent point is an element of the image of chi3. The reason for this is quite cute, is that the proof of this sufficient direction is completely non-constructive, and it relies on an elementary fact of dynamical systems, that if you're dealing with the iteration of a map on a discrete space, like the integers, every point of your space, it comes in exactly 3 flavors. Either it is a periodic point of the map, it is a divergent point of the map, or it is a strictly pre-periodic point of the map, meaning that it is eventually iterated to a periodic point, but the point itself is not periodic. I am convinced that the converse of this result holds. However, at the moment, I can't find any proof to justify it, and it might be that this proof could be quite difficult. Perhaps, though, a greater development of the rest of my PQ-adic analytic techniques might help in resolving the rest of this conjecture. So right now, we're 3/4 of the way to completely reformulating Collatz-type conjectures. So again, that itself is a worthy area of interest that has nothing to do with the Collatz problem itself, but rather with its reformulation. So that's the first asterisk. The reformulation is incomplete. The second is that, as I said, this is very impressive sounding, so you probably don't know what it means, so I'm going to now explain it. So in the beginning, spectral theory meant the study of eigenvalues of matrices. Given an n by n matrix A, we compute the determinant of lambda in minus A, where in is an n by n identity matrix, and then we solve for the roots of the resulting polynomial, while also praying that we're working over an algebraically complete field so that all the roots exist. The more abstract characterization of this process comes from when we remember from linear algebra that a matrix is invertible if and only if its determinant is non-zero. Now, n by n matrices with entries in a field K form an algebra over K. We can add them entry-wise, we can multiply them by scalars from K, and we can multiply matrices by one another. As quantum mechanics reminds us, this algebra is not commutative, but it is unital, meaning it has a multiplicative identity element, and that's the n by n identity matrix In. So if we equip the field K with an absolute value, more on that later, and then stipulate that the resulting metric space we get on the field is complete, we make K into a Banach space. Since as a vector space over K, our matrix algebra, mat n of K, n by n matrices over K, is finite dimensional, we can then use the absolute value on K to give this matrix algebra a norm as well. The simplest of these would be to define the norm of a matrix A as the maximum of the absolute values of its entries. Equipped with this norm, our matrix algebra becomes not just a Banach space, but a Banach algebra. Now, recall here that a unit of an algebra is an element which has a multiplicative inverse. U times U is a unit if there's a element U inverse such that U inverse equals U inverse U equals the identity element of the algebra, the multiplicative identity element. So, in going back to matrices, the eigenvalues of any matrix A are precisely those scalars, lambda, for which lambda in minus A fails to be a unit of the Banach algebra, of our matrix algebra. This then leads to a definition of spectral theory, which works in any Banach algebra with a multiplicative identity. And specifically, let X be a unital Banach algebra over a field K with 1x as its multiplicative identity element. Then, by spectral theory, we mean the study of those scalars lambda in K for which lambda 1 minus chi is or is not a unit of X. Non-archimedean spectral theory, then, means doing spectral theory when our field K is non-Archimedean, such as when K is a field of p-adic numbers. So, to get to the reformulation described in 3, we need 3 main ingredients. The first is, as mentioned, the Newman. In this case, it's the Newman chi3 for the shortened 3x plus 1 map, T3. Chi3 is a 2-3 adic function from the 2 adic integers to the 3 adic integers. And I explained about the character, about the name. So as I mentioned in episode 1, chi3 can be characterized as, and if so defined, if so desires, defined as the unique 2-3 adic function from the 2 adic integers to the 3 adic integers, satisfying the following equations. F of 2z equals f of z over 2, and f of 2z plus 1 equals 3f of z plus 1 over 2. This holds for all 2 adic integers z, but in order to get the characterization property, you also need to subject f to the following limit condition, which I call rising continuity. This is the statement that this is written wrong. This should be the limit as n approaches infinity of f of z mod 2 to the n converges 3-adically to f of z. So in other words, the f of z mod 2 to the n converges 3-adically to f of z. This leads to the I made it screw it up again. This leads to the general definition of rising continuity, which is that if we have P as a prime and let K be a metrically complete valued field, which if you don't know what that is, just don't worry, we'll cover it in a later video. We say that F is rising continuous if the limit as n approaches infinity of F of z mod P to the n converges in the topology of K to F of z. Whereas indicated, it means that the limit occurs in the topology of K. Note that we only require the convergence to occur pointwise. So that's in part ingredient 1. Now, as mentioned in episode 1, the reason why Schickhoff and other mathematicians of the Dutch school of non-Archimedean analysis deemed PQ adic functions less interesting than PP adic functions was because PQ adic functions were far too rigid. As we saw, in PQ adic analysis, a function is integrable if and only if it is continuous, which makes a lot of the questions we would ask in classical analysis simply not relevant here. Well, we will see later on that chi3 is rising continuous, which shows that by relaxing continuity to rising continuity, we can get much more interesting results in PQ adic analysis. If I had to give a big bird's eye view takeaway of my research, it's that rising continuous functions seem to be the more natural candidates to study in PQ adic analysis, because we can get much more diverse results with them as opposed to continuous PQ adic functions. At the moment, there's an asterisk here. While rising continuity seems necessary for getting interesting behavior, I do not know if it is also sufficient. That is to say, I don't know if an arbitrary rising continuous function will give nice behavior like what we saw in episode 1. Indeed, in my dissertation, I had to impose quite a few conditions on my rising continuous functions in order to get something nice out of them, like we got out of chi3 in episode 1. Basically, this boiled down to assuming that our functions satisfied a system of functional equations like chi3 does, and then you could get all the nice stuff. And so again, here's another thing we can figure out. How restrictive do we have to get on our rising continuous functions? How many conditions do we have to impose to get something interesting out of them? And then, once we've done so, how do we work with them as spaces, etc., etc.? So on that note, one reason to care about rising continuous functions is that we can show that the set of rising continuous functions from Zp to K forms a non-Archimedean Banach algebra under the usual operations of pointwise addition, pointwise multiplication, and scalar multiplication. We denote this algebra by C twiddle of Zpk. This is the algebra, again, of rising continuous functions. C of Zpk, meanwhile, is the Banach algebra of continuous functions. And as I showed in my dissertation, C twiddle of Zpk contains C of Zpk as a dense subalgebra. So the closure of C of Zpk in C twiddle is C twiddle. So aside from classifying rising continuous functions in their own right, it also seems like investigating subalgebras and ideals of C twiddle is going to help make progress on Collatz and related problems. In particular, not only does our non-Archimedean spectral theory lead us to studying the ideals of such subalgebras, but it stands to reason that C twiddle and its subalgebras will be necessary participants in any attempt to embed my work in the language of algebraic geometry. In particular, the jury is still out on what the function field of the image of chi3 over the two adics ought to be. Again, just to do a parallel here, the continuous PQ adic functions are too rigid to get what we want. So we're going to have to potentially use some intermediary extension of the continuous function algebra and the rising continuous function algebra, and use that to construct rings of functions in order to then do sheafy, schemy things. So now, definition 6. I've been saying the Dutch school of non-Archimedean analysis, so I think I might as well clarify what I mean by that. I specifically mean the body of work pioneered in the 1960s by W.M. Schickhoff, ACM van Ruij, M. van der Put, and other mathematicians working at the Catholic University of the Netherlands. It's since been renamed, but if you Google Catholic University of the Netherlands, you'll get to the right place. Also, just speaking of which, I cannot. Shikov died in 2014 or 2016, which it was a tragic. But I believe that ACM van Ruij is still alive. I haven't been able to get confirmation of this. I sent him an email, no response. If anyone happens to know if ACM van Ruij is still alive, please let him know about my work. I think he would be interested in it. And I'd just like to know what he'd have to say about it. So these mathematicians were doing their work as graduate students at the time, and they were going about realizing A.F. Mana's hopes, first voiced in the 1940s, of understanding what analysis would be like in the non-Archimedean setting. Just to take a step back, Hensel introduces the p-adic numbers in 1896, and most infamously, he misuses them, messing up arguments with convergence, and partly as a result of that, and partly because ideas of metric spaces and topology in the modern sense had yet to come around, the mathematical community was a bit wary of Hensel's methods. So it took, most famously, it took until the 1920s when Hermann Hesse was walking around in Göttingen. He just found an antique shop and saw Hensel's book on p-adic numbers available. He decided, I need to transfer to Marburg to study with Professor Hensel. And that then led him to discovering the Minkowski theorem about quadratic forms over the p-adics, and it took even a decade later, Haas still had to go around defending the use of the p-adic numbers. So, but that really they began to become accepted into mathematics in the 1930s, and then in the 1940s, what comes along is Mana saying we need to figure out how to do non-Archimedean analysis in general. Now, when I say non-Archimedean analysis, you would be forgiven for thinking that this just means figure out how to do p-adic analysis. Part of the reason why I'm putting so much emphasis in this phrase PQ-adic analysis is because there are really quite a few possibilities that can arise, and just saying p-adic analysis at this point, it's loaded language that isn't clear enough. Here are some of the possibilities we can consider. Here, let x and y be valued fields. If these are fields with an absolute value equipped to them. If we want to do analysis of a function f from x to y, here are the possibilities to consider. I have put in parentheses next to these, I've put the names that I've given them so that we can have everything nicely classified. So, we have the case where x equals y, and both x and y are Archimedean. I call this infinity-adic analysis. Infinity coming from the infinite prime of number theory, but we'll talk about more about that later. Infinity-adic analysis is basically it's all classical analysis. It's real analysis and complex analysis. Then we have the case where x equals y, and both x and y are non-Archimedean. And in this case, I call it p-adic analysis. If you go around and Google what textbook in p-adic analysis, you're going to get most likely a textbook in this subject here. I taught myself the material using Anna Robert's A Course in P-adic Analysis. It's a very nice book, very comprehensive. This subject is probably the most developed form of non-Archimedean analysis, not only because it's used in number theory and algebraic geometry, but because we're working in the same input and output field, we can have analytic function theory. Analytic function theory, by which I mean the theory of power series. In order to have a power series, you need to have the space of the power series coefficients belong to the same field as the space of the power series input variables, or otherwise multiplication makes no sense. So from this we get real analysis has its own analytic functions, complex analysis has its own analytic functions, and p-adic analysis has its own analytic functions. And despite certain differences that occur, there generally, if there is a result in one form of analytic function theory, it's going to exist in another form, in another version of it. However, this is only the tip of the iceberg. Then there's the cases where x and y are different. We can have the case where x is non-Archimedean and y is Archimedean. This is P-infinity adic analysis. This one here was first made famous by the late great John Tate in his famous thesis, a Fourier analysis on number rings. I believe that's the title. What he does is he shows that the zeta function's product formula can be realized as a product, literally, of zeta functions of P-infinity adic type, one for each prime P. This type of analysis is also done a lot in representation theory. There's a book by Donfeld and Hundley, representation theory of, automorphic representations for the general linear group. The first chapter of that book gives a nice overview of P-infinity adic analysis. This itself, it can be considered a more specific case of abstract harmonic analysis, which studies harmonic analysis on locally compact abelian groups. Those are abelian groups that are topological spaces, meaning that the group operations are continuous with respect to the topology, and which are locally compact as topological spaces. You can also further generalize this to non-abelian groups, but then you get into representation theory and it gets more complicated. Now then there's the case where X is Archimedean and Y is non-Archimedean. This is infinity P adic analysis. No one does this, and the reason why is because the only continuous function from an Archimedean field, like the reals or the complexes, to a non-Archimedean field, like the p-adics, the only continuous functions are the constant functions. As we just saw, though, continuous functions are too rigid, so it may be the case that we get lots of interesting theory if we allow ourselves to work with a weakening of purely continuous functions in this case. I haven't explored it yet, but someone could look at that and see what happens. It might be interesting. And then finally, we have PQ adic analysis, which is the study of functions from X to Y, where X and Y are distinct non-Archimedean fields. Now, technically, this picture is actually a lie. You see, I've forgotten to include a very important classification, which is the characteristic of our field. Recall that the characteristic of a field is the number of times you need to add 1 in the field to get 0, and that a field is said to have characteristic 0 if and only if you can never arrive at 0 by adding 1s. Wherever you see a non-Archimedean field in this list, you can consider either a non-Archimedean field of characteristic 0, the p-adics, or you can consider a non-Archimedean field of positive characteristic. These turn out to be fields of formal Laurent series with coefficients in a fixed finite field. And for the record, yes, analysis can absolutely be done in fields of positive characteristic. Kochube has a book on it. It's called Analysis in Positive Characteristic. And so if we had to keep tabs on the characteristics of our field, we would get even more diverse forms. And all of these are distinct. Some, depending on the particular setup, you might get one thing or the other. And when people talk about non-Archimedean analysis in general, it's very unclear what do they mean. Do they mean PP? Do they mean PQ? Do they mean P-infinity? Do they mean PQ for positive characteristic? Etc. This is why I recommend using this terminology, because it's much clearer. And just in case you think that the positive characteristic versus the 0 characteristic doesn't matter, no, in my research it absolutely does, because we'll be doing things in positive characteristic too, eventually. So that's our first part. We have our correspondence principle, which, as I said, it comes in 2 flavors. The one for periodic points and the one for divergent points. This is the CP-PP and the CP-DP. And the CP-PP is a complete bidirectional statement, whereas the CP-DP currently only has one direction proven. So now, just before we continue for the next ingredient in my reformulation, I need to go over a bit of number theory. So recall that the ring of 2 adic integers, z2, is obtained by completing z with respect to the 2 adic absolute value. In doing so, we end up with a variety of new numbers, some of which will be familiar to us, and others which are not. In particular, we have the following fact. Let p be a prime number. Then a rational number r is an element of the p-adic integers if and only if, when written in simplest form, the denominator of r is co-prime to p. So for example, 2/3 would be a 2-adic integer, but would not be a 3-adic integer. As we'll see later on, for every rational number r, there can only be finitely many primes p for which r is not a p-adic integer. This fact comes up in defining the Adel ring I mentioned earlier. So because we can speak of those elements in ZP which are rational, we can talk about irrational elements of ZP as well. This statement here, note that it's an if and only if. So just to understand the implication of this, note that we say that a number r is in Q if and only if there are integers a and b with a not equal to 0, such that a times r plus b is 0. So we can then say definitively without any worry that a rational number is, that a p-adic integer is rational if and only if there are integers a, b with a not equal to 0, such that a z plus b is equal to 0. So just like in classical analysis, the irrational p-adic integers are those whose minimal polynomials over Q have degree greater than or equal to 2. From this, it can be shown that just like in real analysis, when we write our integers in terms of their digits, our p-adic integer will be rational if and only if its sequence of digits is eventually periodic. So just like how pi is irrational because its digits in base 10 aren't eventually periodic, any p-adic integer whose p-adic digits are not eventually periodic will necessarily be irrational. With that review out of the way, we can now state the correspondence principle for T3. The CPPP, for periodic points, a non-zero integer x is a periodic point of T3 if and only if there exists a z in Z2 prime intersect Q such that chi3 of z is equal to x. Technically, I can actually remove the condition that x be non-zero, but it makes things easier if I just leave it out. So here recall that Z2 prime is the set of 2-adic integers with infinitely many digits. That's Z2 take away the non-negative integers. So the periodic points are precisely the rational integer values that chi3 takes over Z2. By rational integer, that's my fancy number theorist way of saying an integer in this set, Z, the integers of the rational numbers. As you said, we can distinguish between rational integers and p-adic integers, so that's why the term exists. Now we have the CPDP. If there is an irrational 2-adic integer Z, such that chi3 of Z is a rational integer, then chi3 of z is a divergent point of T3. So if we can, the converse then is the assertion that every divergent point of T3 is an integer value attained by chi3 over the irrationals. This also then leads to probably the prettiest thing I found in my dissertation, which is that there is a correspondence, the periodic points are precisely the integer values that chi3 attains for rational 2-adic inputs, and the divergent points are the integer values that chi3 attains for irrational inputs, which I think is pretty sweet. So again, I conjecture that the converse of this is true, but I don't know how to prove it. So even in this incomplete state, the correspondence principle is still a powerful result. Rather than study a dynamical system that seems to defy all attempts to understand it, we can use the CP to pass the matter of solving the Collatz conjecture to studying the value distribution of chi3. This is actually very nice because value distribution theory is technically both a matter of algebra and a matter of analysis. Analysis does value distribution theory all the time. Probably the best example of this is Nevanlinna theory. There's an extra A here. It studies the value distributions of analytic functions, specifically meromorphic functions, by generalizing the Poisson-Jensen formula, which allows us to count the number of poles and zeros of our given meromorphic function. What's really nice, though, is, as I said, because this is an analytic function theory thing, it can be done not just in complex analysis, infinity, but it can also be done in p-adic analysis, PP. William Cherry has some notes from one of the meetings of the Arizona Winter School that cover p-adic analytic function theory, and one of the chapters is about Nevanlinna theory. It's quite nice, and it's actually what inspired me to go in this approach partially. So that's the analytic side of Nevanlinna theory. Of value distribution theory. But there's also an algebraic side. Namely, what this shows is that we're studying the values, the vanishing set of a particular family of functions. So if we rewrite this as chi3 of z minus x, that's going to be a function. And if x is an integer, that function will vanish if and only if z is a periodic point or divergent point. Also, just when I'm talking, for convenience, I'm going to treat the converse of the CP-DP as true. So whenever I mention divergent points and periodic points, keep in mind the caveat that the converse has yet to be proven. So we have the vanishing set problem. And in that respect, this is really cool because then we can start using the techniques of commutative algebra, because we can consider the ideal of a certain function algebra, possibly the rising continuous functions. We can consider the ideal generated by this and try and figure out the function field, etc., etc. And that would potentially lead us to being able to do étale fundamental groups and other fancy stuff there. So, and actually this is quite nice. The third ingredient of our reformulation, the non-archimedean spectral theory, the result that I used to do it actually lies quite beautifully in the middle of algebra and analysis. In my dissertation, I proved a novel PQ-adic generalization of the celebrated Wiener-Tauberian theorem, first proved by Norbert Wiener in the 1930s. And it's a crowning jewel of 20th century harmonic analysis. It generalizes the Hardy-Littlewood-Tauberian theorem. It's wonderful, and it's one of those things, and we'll talk about this more in the episode that I have dedicated to it, but it's a perfect example of how, depending on how you state your theorem, it could seem almost trivial or incredibly dense, and it's a chimerical result that has many different formulations. One of the most classical is that it tells the conditions in which one of the most classical versions is that if you have a Fourier series which converges absolutely, then the reciprocal of that Fourier series also has an absolutely convergent Fourier series representation if and only if the original function has no zeros. And it's really nice, and it connects algebra, specifically the invertibility of elements of a Banach algebra, with analysis. Fourier transforms, Fourier series, L1 spaces, L infinity spaces, L2 spaces, etc. It's very nice. So for now, though, the main idea is this. This correspondence principle tells us that in order to understand the dynamics of T3, for example, it suffices to know the rational integer values that chi3 attains as z varies through z2. So if we just let x be an arbitrary integer, we know that since chi3 is rising continuous, and since all continuous functions are rising continuous, and since the rising continuous functions form an algebra, then this thing is going to be rising continuous too. As such, we can consider its reciprocal. Note that if x lies in the image of chi3, this function is going to blow up when z makes chi3 equal to x, and if if x is not in the image of chi3, this function won't blow up. So the values of x in the image of chi3 are precisely those x's for which this function is not a unit of our Banach algebra. This is spectral theory. This is a Banach algebra. It has a unit. Its multiplicative identity element is the constant function 1, and so we can study the multiplicative invertibility of elements of this form. So in that sense, the spectrum of chi3 in here, the algebra of rising continuous functions from the two adic integers to the three adic complex numbers. That's the metric completion of the algebraic closure of the field of three adic numbers. So the spectrum of chi3 is precisely the set of scalars for which this thing is not a unit. Thus, by characterizing the value distribution, the values attained by our function, that's the same thing as characterizing its spectrum, doing spectral theory. So since the Fourier transform is a homomorphism of Banach algebras, this is the convolution theorem, which says that that the product of two functions, their Fourier transform, is the convolution of their respective Fourier transforms. The Fourier transform turns multiplication into convolution and convolution into multiplication. So with this, the Wiener-Tauberian theorem that I proved boils down to the following equivalence. Chi3 of z minus x has a multiplicative inverse in C twiddle if chi3 hat of t minus x times the indicator function of 0 of t has a convolution inverse, meaning that we can convolve something with this to get the this function here, which is the indicator function of 0. It is the identity element of the convolution algebra we get by applying the Fourier transform to this algebra. In particular, the statement has a convolution inverse will be realized as the span of translates of chi3 hat of t minus x times 1, 0 of t are dense in C0 of z2 hat C3. This is the Banach space of functions from z2 hat, that's dyadic rationals in the unit interval with addition modulo 1, to the three adic complex numbers with the property that as the two adic absolute value of t goes to infinity, the three adic absolute value of f of t converges to 0 in the topology of the real numbers. This much to my disappointment, when I was attempting to submit my proof of the Wiener-Tauberian theorem to a journal of p-adic analysis, they did not understand what this notation meant. So for anyone who wants to know, it means for all epsilon greater than 0, there is an n greater than 0, such that f hat of t will have a three adic absolute value less than epsilon for all t in z2 hat, whose two adic absolute value is greater than 2 to the n. So by studying chi3 of t, chi3 hat of t, chi3 hat of t minus x, 1, 0 of t, and their translates, we can then determine whether or not chi3 of z minus x is a unit in the algebra of rising continuous function, which then tells us whether or not x is in the image of chi3. We can actually then take things further, because when you unpackage this question, it then takes you to a study of I'll save it for later. Let it be a surprise. So in summary, what have I done? The periodic points and divergent points of T3 are controlled by the rational integer values that chi3 takes over the two adic integers. Chi3 is an element of this Banach algebra of rising continuous functions, and so the spectrum of chi3 is then the scalars lambda, such that chi3 of z minus lambda is not a unit of this algebra. This function right here is not a unit of the algebra if and only if lambda is in the image of chi3 over z2, and we can determine whether or not chi3 of z minus lambda is a unit of the algebra by studying the span of the translates of its Fourier transform. Now, so that's pretty nice, pretty big, pretty fun. It alone would probably make for a nice full year-long course to study. However, we can go much, much further. So in my dissertation, rather than considering just the Collatz map, I considered a family of generalized Collatz maps I call Hydra maps. In addition to doing math, I also write fantasy/science fiction, so I like naming things coolly like this. It seems like only other writers who know about mathy stuff seem to appreciate the name, but trust me, it's a cool name. So the name is due to the Hydra-like appearance of the certain visualizations of the orbit classes of the Collatz map, as well as the difficulty of defeating the Hydra of Greek myth. The Lernaean Hydra, remember, Hercules had to defeat it with help from his charioteer. He used poison, and then he cauterized the decapitated heads, then the necks of the Hydra, so that the immortal heads could not grow back. that the mortal heads could not grow back, and then he cut off the immortal head and buried it under a rock. So hydras are really hard to conquer, and thus the name. Now, this is probably one of my favorite pictures of the Collatz conjecture. Yes, this is a picture. It's not a seaweed or something. Here is one, and each node, each branch on this diagram represents an individual integer. We connect two integers m and n if and only if either the Collatz map sends m to n or n to m. The lines are between two numbers are then tilted left or right based on whether, as we move to the left toward 1 at the end, whether we go from, it's tilted up or down based on whether we go from an even integer to an odd integer to an odd integer to an even integer. Then a nice color gradient was applied to make it look pretty, and we get this. Conjecturally, if the Collatz conjecture is true, this tree should go on to contain all positive integers. Yeah. So this shows the trajectories of, if I recall correctly, the integers from 1 to 50,000. So here, my definition of Hydra maps are as follows. Technically, I'm going to be working with p as a prime number. The theory that I'm going to present can be made to work when p is composite, though it will entail certain technical complications. So for simplicity's sake, let's just focus to prime numbers p. Also, remember that the triple bar with a p on top means congruent modulo p. So let p be a prime number. Then a one-dimensional p-Hydra map is a map H from Z to Z of the following form. Here, so we have, I call these individual maps the branches of H. And here, AJ, BJ, and DJ are integer constants with AJ and DJ greater than or equal to 0, so that the following two properties hold. The AJs and DJs are coprime, and for each j, the output is an integer if and only if n is congruent to j mod p. These maps do technically have a pre-existent name, but it's horrible. It's residue class-wise affine maps, RCWA. If you type that in, RCWA maps, you'll get a nice online textbook that has lots of computations featuring examples of them. It's very comprehensive. But again, RCWA, it's just a mouthful. Hydra maps is much cooler. So I define HJ as a map on Q, as HJ of x equals AJX plus BJ over DJ. I know this is going to make algebraists angry, but I just write this notation to mean this set because I'm lazy. We'll occasionally think of this as an actual group with its additive structure, or as a ring with its additive and multiplication structure. But if I ever write this and you don't know what it means, it just means 0 to whatever this number is minus 1. So note here that the branches, I define them over Q. It's going to be important in my work to consider the action of these branches separately. So the definition that I'm giving here is slightly less general, slightly more general than the one that I gave in my dissertation. In my dissertation, 2 requires not just that this be an integer, but that this be a non-negative integer. The reason for this is I was basing it off the Collatz map. The Collatz map fixes 0. It sends negative integers to negative integers and positive integers to positive integers. So I was going to decide to work with maps of that type. However, for simplicity and comprehensiveness, we can drop that condition. I have then introduced the terminology of rotational. So H is irrotational if for each j, if the branches send positive integers to positive integers and negative integers to negative integers. And I say H is rotational whenever it is not irrotational. So if I had to give one word of advice to anyone studying Collatz and other Hydra maps, it would be this. Collatz-type maps need to be studied in relation to other maps of their type. So the Collatz map needs to be studied in relation to other maps of its type. Doing so is the only way we can figure out whether our observations of the Collatz map and its dynamics are actually significant and have bearing on the map's conjectured behavior, or if they're just mathematical coincidences. Beyond this, it is also highly desirable to have a unified formalism for working with maps of this type. At present, Collatz studies are lost in a sea of different notations and formalisms, most of which are not readily compatible with one another, and not to mention quite ugly too, with all the indices, ad hoc statistics, and so on and so forth. To make matters worse, we'll have the cranks who will come in, claim they've invented some completely new theory of math using pictures or beads or tiles or whatever, and it's very difficult to negotiate all this. And part of the reason why the Collatz studies it languishes in the mathematical ghetto, is that there's no unifying formalism and everyone's wasting their time studying just the classical Collatz map, when what we really needed to do is build a theory that works for all of them. So, as I showed in my dissertation, the correspondence principle, as we have seen for Chi3, it works for basically all of the Hydra maps. These Hydra of the type considered above. These maps have Neumans, and their Neumans satisfy correspondence principles. In fact, and this is quite funny, the scope of the results I give in my dissertation, like the version that you can find on my website, it is not as big as it could be. So, it's worth explaining this because, as I said, it's a bit of a funny story. So, in my dissertation, I saw that, consider a Hydra map like this. This is a 3 Hydra, which sends n to n over 3, 5n plus 1 over 3, or 7n minus 1 over 3, based on the value of n mod 3. So I would call this type of map a polygenic map, because of the fact that these coefficients here, I have 1, 5, and 7. This would be monogenic if the coefficients were either 1 or 5 and 1 or 7. The fact that we have 2 different prime numbers occurring here makes things complicated. It would also work if 7 was replaced, say, by 25 or 10 or some other number that's a multiple of 5. So my construction of Chi3, as we will see in episode 3, came about from considering what happened when we considered arbitrary sequences of compositions of the even and odd branches of T3. So note that the odd branch is actually 3-adically contracting. If we subtract it, it's a Lipschitz continuous with a Lipschitz constant of 1/3. So what we have here is 2 contracting maps, except they're not contracting in the same topology. This map is contracting in the Archimedean topology, the real topology, whereas the odd map is contracting in the 3-adic topology. I'll talk about this again later, but studying the images of successive applications of 2 contracting maps, or 2 or more contracting maps on a metric space, that's a well-established thing. It's called a de Rham curve, after the Georges de Rham, the de Rham of de Rham cohomology. It's a very nice thing, and you can basically view my construction of the Neumann as a generalization of that to the cases where our maps are contracting, but not necessarily all in the same topology. So in this case, we have a map which is contracting 5-adically. Here, this is contracting infinity-adically, meaning with respect to the real topology, and a map which is contracting 7-adically. I wasn't able to deal with this polygenic case in my dissertation, but I was able to deal with this monogenic case. So I thought that the polygenic case, the reason why I couldn't deal with it, because it would be the contractions wouldn't all occur in a single topology. It wouldn't converge. In particular, I found a way to handle the fact that this converges in the real topology and this converges in the 3-adic. That was manageable, and it has to do with the fact that this map fixes 0. But in this polygenic case, it's no longer tenable. It didn't work. However, 2 weeks before my dissertation was due, in March of 2022, I suddenly had a revelation. Originally, I came up with frames as just a shorthand. I was doing my computations just as I did in episode 1, and instead I got sick and tired of having to write at the end of every proof where the topology is in the real topology if z is in the non-negative integers, and is the q-adic topology if z has infinitely many digits. So I just said, fine, I'll write f2q if the convergence is happening in that form, and that was just a convenience. However, 2 weeks before my dissertation was due, I was going through rewriting just cleaning up my proof of the correspondence theorem, and I realized that frames could be used to handle the polygenic case. I show an example of this in my frames paper, and it gets quite intricate, but the point is, once I freed myself from the convention of having to keep my function's domains in a single topology, and instead have a mix and match of them, I could make sense of all of these different maps. I have not written out the details of how the correspondence principle and everything applies in the polygenic case. However, it isn't really necessary. The proof as written and in the article that I currently have published, the part 1 of my Collatz Conjecture and Non-archimedean spectral theory series, which I have linked at the bottom of the description, the proof I have in that paper, and which is the proof that I'm going to be showing you in episode 3, that proof can be adapted almost verbatim to the polygenic case. Just requires being a little bit more careful about what topology you're using. But all of it carries over verbatim, and it's wonderful, and it's great. But just the polygenic case alone is by no means the final frontier of my research. We can go much, much deeper. So my Newman method admits a straightforward generalization to Collatz-type maps defined on rings of algebraic integers, also called number rings, such as Z adjoin root 3. The first example of such a map, in fact the map is on Z root 3, is given by Ley in 1983. An account of it and the other maps of that type can be found in K.R. Matthews' excellent PowerPoint slides about Collatz-type maps. I've included the links in the description. My formalism treats Hydra maps of this type as multidimensional, and do you know that for technical purposes, I'm giving the definition of my multidimensional Hydra maps in terms of the ideals of a number ring, but in practice, I'll often work with affine linear maps on Z to the D, particularly when doing Fourier things. This is because, recall, a ring of algebraic integers like this is isomorphic as a ring with a basis to the lattice ZD. We just pick a Z basis for this ring of integers. So here's the definition of a multidimensional Hydra map. Again, this is defined using number rings rather than lattices. Let F be a number field of degree D over Q. When D is 1, we obtained a Hydra map on Z by defining what H does to a given input n based on the value of n modulo some prime p. The natural analog for this procedure in multiple dimensions is a map on OF, the ring of integers of the field F, whose action on a given F integer Z is determined by the value of Z modulo I, where I is some proper ideal of OF. This generalizes the D equals 1 case, where I is the ideal of Z generated by the prime P. So fixing a non-zero proper ideal I of 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 index iota. Index, recall, is the number of elements in the quotient ring OF modulo ring modulo ideal. So index I, the structure theorem for finitely generated modules over a principal ideal domain, tells us that there is an isomorphism of the additive groups of OF mod I is isomorphic to the product of the additive groups Z mod Pn Z, where R is between 1 and the index of our ideal, and where the Pn's are integers greater than or equal to 2, such that Pn divides Pn plus 1 for all n from 1 to R minus 1. R does not appear to have a standard name in the literature, so I call it the depth. And note here that R is always going to be at most D. I then write I0 through I iota to denote the cosets of I in OF, with I0 denoting I itself. With all that said, an I Hydra map on OF, or more succinctly, an I Hydra map, is a surjective map on OF of the following form, that it's an affine linear map that we apply depending on the value of the input modulo I. Here, the A, J's, BJ's, and DJ's are F integers, such that here they're non-zero. The GCD is 1. The ideal, the DJ's generate in OF is contained in I, and this here we have the integrality condition. These are the direct multidimensional the number ring analogs of the properties for one-dimensional Hydra maps. I then define the depth of H as the depth of this ideal I. By appealing to the power of linear algebra, we can then realize H as a map on the lattice Z with branches of the form the D tuple X gets sent to dj inverse times ajx plus bj for invertible d by d matrices dj and aj, and for d by 1 column vectors bj. To do this, note that there is a set B in OF which forms a z basis of the additive group of f integers, so that for any element z of OF, the image of z under the projection from OF mod I to Z mod PNZ is the value of XN mod PN. In other words, I'm picking a basis such that in order to figure out what H does to X, you just look at the values of each coordinate modulo PN. So I choose once and for all such a basis B, and then we make the identification as everything is nice. And in this case, the elements J are no longer, J's are this is a leftover, so just ignore the strings, that'll make sense later. So instead of picking J's being subscripts, like we had the 0th map, the 1th map, our J's are going to correspond, each branch is going to correspond to some J in this set, which is my notation for this product right here. So instead of indexing our J's by the values like from 0, 1 to P minus 1, we're going to be indexing them over quotient of the lattice like this. So that being said, a d-dimensional P Hydra map is then defined as a map of the following form. It's H of X, where we sum over all of the equivalent, basically it's all J where the Pnth component of J ranges from 0 to Pn minus 1. And then this is Iverson brackets, and this notation here is my shorthand for the system of congruences. X1 is congruent mod P1 to J1, blah, blah, blah. XR is congruent to JR mod PR, and this is going to be 1 if these congruences are satisfied, and 0 otherwise. So, again, like with the one-dimensional case, this definition here is slightly more general than the one I gave in my dissertation. In my dissertation, I imposed some additional requirements that reflect the two-sidedness of Hydra maps on Z, like the Collatz map. And in this case, this leads to a generalization of the idea of irrotational or a rotational Hydra map on the one-dimensional case. And my part 1 paper covers the details of this. So, as I showed in my dissertations, my methods, they don't just work for one-dimensional Hydra maps, they work for multi-dimensional Hydra maps too. However, like with the one-dimensional case, I was initially flustered by the polygenic case, so my dissertation only deals with the monogenic multi-dimensional case. But like with the one-dimensional case, you can use frames to easily make sense of the polygenic case, and everything's nice. So here, I'm going to give an example. I found this example on Reddit by Actaeon H. They made a post on the math subreddit, and I've linked the post in the descriptions. It contains several examples of multidimensional Hydra maps, along with some lovely images Actaeon H made of their orbit classes. So here, let D be the map on the Gaussian integers. It's D for dragon, defined by the following. D of Z is Z over 1 plus I if Z is 0 modulo the ideal generated by 1 plus I, and we add I otherwise. Note that 1, 1 plus I is a Z basis for Zi, and on writing 1 over 1 plus I as in negative I over 2 times 1 plus I, we see that given any A and B and Z, the action of an element Z written in this respect to this basis by dividing by 1 plus I is this thing. And so the Gaussian integer A plus B times 1 plus I will be a multiple of 1 plus I if and only if A is congruent to 0 mod 2. So now using coordinates from our basis B, given as a Gaussian integer Z, I will write it in vector form as xy to mean that Z is equal to x plus y times 1 plus I. we can then define the lattice analog of D on Z2 by D sends Z's B coordinate vector to D of Z's B coordinate vector. Then going through the computations, blah, 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 just work everything out, write things in basis, break it up into coordinates using this formula, we end up with the following, that D sends xy to this matrix times xy if x is even, and this if for all other possibilities of x and y. So note here, this map has 4 branches, one corresponding to the choices of x and y, x mod 2, one corresponding to the choices of y mod 2. Of these branches, 3 are identical. A little rewriting then gives us the dj inverse aj plus bj form, which is this thing. And here's the picture provided by Actaeon H of the orbit classes of this map. This is the two, this should say I, this should be I know this should be a C and there should be no citation here, sorry. So this is the orbit classes in the complex plane. Here, their 2 fixed points are 0 and the cycle 1 plus I, comma 1. And this is colored based on whether they go. This is proved by establishing the following easy estimate. And that is goodbye Reddit. So this is the lim sup of the Archimedean absolute value of the nth iterate of D is less than or equal to this formula, which is 1 over the square root of 2 mod 1. And so because the D is acting on a discrete space and its iterates are always bounded, it can have only finitely many orbit classes, and then it's easy to show that there are just 2 of them because these are the only fixed points or these are the only periodic points with radius at most this. So here the elements, the picture we see, this is 0 if it's white if it goes to 0 and blue if they're iterated to the cycle. This picture, the reason why I call it D is because we see the famous highway dragon curve present, and there is the emergence of this curve from the map is easily seen if we choose a different set of coordinates, namely this set of coordinates. The corresponding realization dB ends up being the following. And here again, this time we're indexed by the values of x and y. And note that this matrix here is 1 over root 2 times a counterclockwise rotation by 45 degrees around the origin. The classical highway dragon curve is the limit set, that is the de Rham curve, generated by arbitrary compositions of these 2 maps here. So we see that F1 is present in D, albeit with a translation, and that's why we get the dragon curve. Very pretty. Also, this map here is somewhat degenerate in that it is, here this part is contracting, but this part is neither contracting nor expanding. It's the translation map, which is why this map's behavior is much easier to study. The other maps that Actaeon H featured, they all are defined on rings of cyclotomic integers. He has one with a primitive third Z of primitive third root of unity, and they're very nice to study because they have these easy properties. So studying these would make for an excellent test case and toy models to play around with. Because again, the Newman formalism, it works here too. And because of the nature of this particular map, because it's not expanding, it's even nicer than what we get in the case for Collatz. In particular, so due to the simplicity of the formula used to define D on Zi, this was one case where working with matrices might complicate things a little bit more than necessary. So the Newman of D, denoted chi D, ends up being a complex valued function on Z2, and it actually ends up being an L1, by which I mean it is the space of absolutely integrable complex valued functions on Z2, where the integral is with respect to the real valued 2-adic Haar probability measure. And specifically, chi D of Z converges in C pointwise for Z2 take away S, where S is the measure 0 set of Z's such that the lim sup of the number of 1s in Z mod 2n divided by n converges to 1. That is to say, the singularity set is precisely those Z's, 2-adic integers Z, who their 1s, the 1's digits, have an upper density of 1 in the set of their 2-adic digits. Chi D then satisfies these functional equations on the set of points, a set of z at which it converges, and satisfies the rising continuity condition, which here is said correctly. It's the limit of, as n approaches infinity, of chi d of z mod 2n. Chi d also satisfies the correspondence principle. As we'll see in episode 3, the proof is very nice and really can be easily adapted to any topologically complete valued field. So the fact that chi d is complex valued while chi 3 is three-adic valued is not at all surprising. This is due to the frame theoretic nature of my approach. That is to say, we utilize any viable absolute values on the Newman's output in order to make said output meaningfully fully convergent. So part of what makes me so excited about my findings is that my work extends, as I said, almost verbatim to the multidimensional case, and the correspondence principle, even the computations we did in episode 1, all of them have direct analogs in the multidimensional case. I corresponded with K.R. Matthews back in 2017, and he told me that the multidimensional Hydra maps are basically entirely unstudied. The only studies of them that have been done are Lay's study and the one that Matthews notes. The rest, it's completely unknown, and my techniques can be used. And it's, again, the formalism is the same for the one-dimensional and the multi-dimensional cases. The only way the multi-dimensional case is different is that you're using matrices and vectors instead of scalars, so you have to be careful about the commute whether or not the matrices commute, but otherwise it's almost exactly the same. So acting on H's maps, and I give the link to his post in the descriptions, it might be a great place to start developing this theory. We're not done yet, though. We can still go further. Everything we've talked about so far takes place over fields of characteristic 0. But why stop there? Why not consider what happens in positive characteristic? And so Matthew's slides show that one can get Hydra maps on spaces of positive characteristic. Here, the space we will work over is the ring of polynomials with coefficients in a finite field. I didn't bother to address these in my dissertation. I already had enough on my plate. But as with all the other generalizations I mentioned so far, everything that I've done can be modified easily to show that it's true. We get the correspondence principle. We get the Fourier analysis. Everything is wonderful. Matthew's slides present the following example of a positive characteristic, a Hydra map. Here, f2 of x is the ring of polynomials of the indeterminate x, with coefficients in the finite field with 2 elements. Here it's the t of f is f divided by x if f is congruent to x mod 0. F is congruent to 0 mod x, and x squared plus 1 times f plus 1 over x if f is congruent to 1 mod x. The Newman of this map, chi t, accepts an element of z2 as an input and produces as an output an element r, the ring of the completion of the field of rational functions with coefficients in f2 with respect to the absolute value induced by the valuation associated to the prime ideal x minus 1. A bit of algebra shows that this ring is isomorphic to f2 of y, the integer ring of f2 of y. This is the this is the field of formal Laurent series in Y with coefficients in F2. This is the field of the ring of formal power series in Y with coefficients in F2. And then chi t is the unique function from Z2 to R, so this, Z2 to this, satisfying the following functional equations subject to the rising continuity condition there, where the convergence is in the topology of R, or if the reader prefers, the topology of the field of fractions of R. The isomorphic copy of chi t taking values in F2 of Y can then be written as like this, and is the unique function from Z2 to F2 of Y, satisfying these functional equations, subject to the rising continuity condition, blah. So it's just replacing y with x plus 1 yields the previous version. It would be interesting to see if the number theoretic rule of thumb that function fields are easier to work with ends up being true for the Collatz-type conjectures as well. Note that this is technically a one-dimensional example of a positive characteristic Hydra map. And yes, we can do multi-dimensional positive characteristic Hydra maps too, and everything works there as well. So this is a lot of detail, and this is one of the things that makes me kind of freak out when I heard that my editors of the journal recommend that I should publish my work as a textbook, because I could do a textbook for each of these. And because there's a lot that I'm doing, and because I want to be both comprehensive but also clear, I am hesitant to write up a textbook that tries and deal with all of these cases simultaneously using just one go through. That would just be too much for me. I would need to break it up in different cases, because there's enough subtleties that occur in when you move from the one-dimensional case to the multi-dimensional case, or the positive characteristic to the zero characteristic to positive characteristic, that I'd like to treat those separately. So I might end up having to write the same textbook multiple times. So rather than just start that, I'm going to say, what the hell, let me just make a video and see what happens. So as we can see, there is a vast amount of generality to be studied here. And again, the PQ-adic phenomena that we saw in episode 1, for each of these cases, we get an analog of that, and we can study that too. So as a result, for this series of videos, instead of doing all of this very scary, very general stuff, I'm going to focus on what I basically have considered the ideal test case, which is the shortened QX+1 maps. These are what happens when we take the shortened Collatz map and replace the 3 with an arbitrary odd prime Q. The TQs are an ideal toy case for the more general theory that I've talked about above. They allow us to get variable behavior by allowing the Q to vary, while also keeping those same variations under the control of the single parameter Q. In this regard, we actually end up with a direct parallel with the idea of a bifurcation of a dynamical system, where one has a differential equation that depends on some parameters, and as the parameters change, the long-term behavior of the system may change as well. Indeed, we see that you basically get two cases in this setup. One when Q is 3, and another when Q is greater than or equal to 5. You could also get a case where Q equals 1, in which case you would use you would use a 2 infinity adic analysis rather than 2Q adic analysis. And it is actually very instructive and enlightening to treat Q as a parameter, taking values not just in primes, but integer values, or rational values, or real values, or even complex values. And it actually leads to the idea of thinking about this not as a collection of maps, but rather a single map parameterized over Q. And that's part of where I'm thinking that there might be connections to scheme theory in that language. So the shortened QX+1 maps are not entirely unstudied. After T3, T5 is also known as the 5x+1 map, is probably the second most well-studied Hydra map, and it is somewhat infamous for how ridiculously just contrasting its behavior is compared to T3. So people think that the Collatz map is bad. They haven't met the 5x+1 map. So in the 1970s, Riho revolutionized the field of Collatz studies by introducing the parity vector. This is a groundbreaking probabilistic tool, which what you do is you study the value of an individual iterate modulo 2. So you keep track of how it flip-flops from even to odd. And using this, in 2 papers, he proved that the set of all divergent points of T3 in the non-negative integers has density 0. Recall this means that the number of elements, so recall that given a set S, the density is the limit as n approaches infinity of the number of elements of S less than or equal to n divided by n. It is an unfortunate truth that not every subset of N0 has a well-defined density. So to that end, Terrace's result is groundbreaking in 2 reasons. Not only does he show that he shows that the divergent points has a well-defined density, and furthermore that density of 0 is 0. Those same techniques can be used to show that the set of all divergent points of T5 in N0 has density 1. So for the T3, we expect almost no integer to go to infinity, whereas in T5, we expect almost every integer to go to infinity. However, and this is very mortifying, we have not proven that even a single number goes to infinity. The smallest no integer suspected to go to infinity is 7. Though, of course, no proof of this is actually known. This same preponderance of divergent points also applies to TQ when Q is greater than or equal to 7. Just like chi3 being associated to T3 as its Newman, we can associate the Newman chi-Q to each TQ, and as one would help, and as I've been saying all along, we get all the same things. We get our characterization by functional equations, and by the incorrectly written rising continuity condition, and then we get our correspondence principle, which for some reason is very bigly spaced out. So here, again, the periodic points of TQ are in a bijective correspondence with the set of rational two-adic integers with infinitely many digits that chi-q sends to integer values. And if there is an irrational two-adic integer at which chi-q attains a rational integer value, then chi-q is a divergent point of TQ. So for chi3, we should expect that this never happens. Whereas for chi-q, we should expect that this almost always happens. So that means we would expect that chi-q for q greater than or equal to 5 would have very many integer values attained, whereas chi3 would have very few integer values attained. Also, just notice that this method, my result, the correspondence principle, it doesn't just apply to the non-negative integers, it also applies to the negative integers. So it studies the map that you're working with on the entire space. So, as we will see, the PQ analytic setting utilized in this series is filled with oodles of interesting, tractable secondary and tertiary problems worthy of exploration in their own right, independent of their potential applicability to chi-Q and Collatz. While it would be ideal if proving Collatz was simply a matter of developing a sufficiently good understanding of PQ-adic analysis, the only way to truly know what ingredients are needed to resolve Collatz is if we succeed in answering the conjecture once and for all. Even so, this ought to have no bearing on whether or not PQ-adic analysis itself is worthy of study. It is a new subject with tantalizing mysteries and unexpected connections all its own, and that, in and of itself, I think, makes it deserving of our attention. And I'll hope that you'll join me in episode 3 to continue the journey. That's it for now, and have a good night. Bye.